Sure is a repeat of last Monday. Many of you guys were out for spring break. So this, in fact, it works out perfect because Boston was the only school here on Monday. You guys will pick up with what they did last week. Just a little note, if you are still working on Unit 3 test, please make sure you have that finished so it can be to me by this Wednesday, because I'd like to be able to answer any questions on that in this Wednesday's class. So anyway, we've talked about graphing equations. We made the tables, picked values for x, filled in values for y, and then we made our graphs from that. And remember, from those tables, once we had plotted points, we used the points that we had on the graph to decide where we needed more points. So we might have to extend our tables and put in more values for x and get more y values to get enough points to figure out what shape our graph made. Well, there are 4 real typical shapes for a graph. One is a line. Pretty simple. Either be an increasing line, decreasing line, and it can be more or less steeper or shallower based off of that. We can have a parabola that we saw. We actually had, we only had time to get to one example of a parabola. Kind of this U-shaped graph like that. There's something called a cubic curve. And a cubic kind of looks like half a parabola, then the other side is flipped over, like that. And then there's an exponential. An exponential curve, either is an increasing exponential like this, where it starts out with a very small slope and then takes off rapidly, or like this, where it's decreasing very quickly and then levels out. In the medical fields, well, in any field, linear curves are very important, and parabolic curves are very important. Linear curves are for any sort of constant rate of change. All of our IV flow rates are constant rates of change. It can graph the amount of medication that's been administered to the patient, or it can graph the amount of volume remaining in the IV bay. Anything that involves a rate of change, like a speed, could be graphed with a line. And like I said, anything with that constant change over time. Parabolas are important because they're really the heart of maximization and minimization problems, dealing with the point of the parabola being that maximum or minimum point. Cubics aren't so important in medicine, but exponential curves are huge in medicine. These are our growth and decay models. If you look at bacterial growth, they would follow an increasing exponential curve like this. And decay, like radioactive decay or the decay of certain minerals that come into your body, they'll decrease in an exponential decay model like that. Well, today we want to focus on lines, or what we call linear equations. And from the examples we saw, 2 weeks ago now, we can look at an equation and tell if it's linear by looking at something called the degree of an equation. The degree of an equation is just the highest power on the variables. And usually we're looking at the independent variable. If you recall, when we talked about our graph, The independent variable was the horizontal variable. Typically, that's going to be our x variable. If you notice when we graph, all of our equations were of the form y equals. So we're going to stick with that form for our discussion today. So when we talk about degree, we're obviously not talking about the y variable because it's always going to have a power of 1. We don't write it, but the power there really is 1. So what we're talking about with degree is we're talking about the power on the x variable. If the degree is 1, that makes it a line. The degree is 2, in other words, the highest power on that x variable is a 2. That makes it a parabola. Any higher powers cause it to be different shapes as we go up. 3 would be that cubic curve. Now, things we should be careful of, a root is technically a power on the variable. A square root of x is the same as saying x to the power of 1/2. So if there is a square root, a variable or x inside of a square root, that changes the shape. So we have to avoid that. So anyway, we can identify if an equation makes a line by seeing that it's a degree of 1. In other words, the only power on the x variable is a 1. So let's take a look at some of our shortcuts for graphing those lines, where we look at the simplest linear equations we can possibly find. The simplest one I can think of is just the equation y equals x. And we're just going to make quick little tables. Let's do, if x equals -3, well, y equals x, so y would have to be -3. That'll give us a point right there. If x were 0, y would also have to be 0. That'd be the origin. If x were 3, y would be 3. That would be right up here. So it gives us that line going through the origin. Remember, we said this point here in the middle is the origin, because everything starts there. Goes through the origin and kind of at a 45-degree angle across, corner to corner across the graph. Now remember, we said we can do anything to build onto our equations. Any of our operations: add, subtract, multiply, divide, powers, roots, exponentials, logarithms. Well, exponentials would give us that exponential curve, so we don't want that. Powers and roots would make it not a degree 1 equation, so that would make it not a line anymore. So we're stuck with adding, subtracting, multiplying, and dividing, our big 4 operations. So let's start with adding. Let's do y equals x plus 3. So now if we do our table, if x is -3, well, -3 plus 3 is 0. So -3, 0 would be right there. If x were 0, 0 plus 3 would be 3. That'd be right there. And if x were 3, 3 plus 3 would be 6. So 3, 6 is going to be right there. Read that line. Looks like that. It goes across our graph at the same angle. We can see that the only thing that's changed has been moved up 3 units. So we can see here that adding 3 to our x, to our variable, just moves the line up 3. So that might make it predictable to what would happen if we did y equals x minus 2. If I have my values of x and y, if x is -3, well, -3 minus 2 would be -5. That'd be down here. If x is 0, 0 minus 2 would be -2. That'd be 0, -2 is right there. If x is +3, 3 minus 2 is 1. That's going to be right there. So there's that line. Again, notice it's the same angle. It's parallel to that original line. It's just instead of going through the origin, it's down 1, 2 units from the center. So adding or subtracting to our x moves our line up or down on our graph. Let's look at what happens if we do y equals 2x. So if I make my table here, x and y, if x is negative 3, 2 times negative 3 would be negative 6. So negative 3, negative 6, right there. If x is 0, 2 times 0 would be 0. That's 0, 0 right there. And if x is 3, 2 times 3 would be 6. So 3, 6, right there. So our line goes to the origin again. What has changed is the angle across the graph. It's a steeper angle now. If we want it to be less steep, it makes sense, then we would divide. If multiplying makes it more steep, division should make it less steep. Well, instead of dividing, we could do y equals x divided by 3 like this. But what I'm going to do is this. I'm going to do y equals 1/3 times x. I'm going to multiply by the fraction. So I do my table, x and y. If x is negative 3, 1/3 times negative 3 is negative 1. That's a point negative 3, negative 1. If x is 0, 1/3 times 0 is still 0. So it still goes to the origin. If x is positive 3, 1/3 times 3 is 1. So it's right there. There's our line. You can see it definitely makes it shallower, a lower angle across the graph. Well, so far, as we go left to right, all of our lines have been going uphill. This is what we refer to as increasing. Typically, basically what it's saying is as the value of x gets larger, the value of y gets larger. How could we make it decreasing? Well, our only option that we really have left is this one. Y equals negative 2 times x. So we're multiplying by a negative. And as we set up our table, if x is a negative 3, negative 2 times negative 3 is a positive 6. Negative 3, positive 6 is there. If x is 0, negative 2 times 0 is still 0, so back at the origin. If x is 3, negative 2 times 3 is negative 6. Over here. Something like that. So that gives us what we would call a decreasing line. As x gets bigger, y actually gets smaller in that case. So as we saw, there's only two things that can happen to our line. It can move up and down from the origin instead of going through the origin, or the angle can change. So if I have something like y equals 2x minus 3, I know that the minus 3 here means instead of going through the origin, I go down 1, 2, 3, and the line goes through that spot. I also know that this 2 that multiplies the x changes the angle, makes it steeper. So what we need to do now is we need to define what does it mean to be steeper. Well, it's called the slope. And slope is a ratio of rise over run. So here, 2 is not a fraction, but we can make it a fraction by breaking it 2 over 1. So that's a rise of 2 and a run of 1. So from this original point that we got from here, that starting point, we go up 2, we rise 2, and we go over 1. We run 1. Now we can see the line goes through those points. So this number is called the slope. This number over here is called the y-intercept. Intercept and intersect sound a lot alike. Kind of similar meaning here. It's where it intersects or crosses the y-axis at negative 3. So if we have y equals 2/3 x plus 1. What that's telling us is on our graph, we start out at plus 1. Right there is our first point. And the 2/3 multiplying the x, that's our slope. So 2/3 means we rise 2 and we run 3. And that gives us our second point on the line. So our line goes through those 2 points. Now, if those points are kind of close together, if I wanted to, I could have done it again. I could have rose 2, run 3 again, get a third point on the graph. and use those 3 points to draw the line if I feel better by getting more points on there. We might have y equals negative 3/4 x plus 5. So again, the 5 here is telling us we go up 1, 2, 3, 4, 5 from the origin. That's our starting point. That's our y-intercept, where we cross the y-axis. Now we have a slope here of negative 3/4. The negative on a slope always goes with the rise. So instead of going up from that point, we go down 1, 2, 3. Our run, however, still goes left to right. So 1, 2, 3, 4 is our run, takes us to our second point. Our line goes through those points. Some people get confused if the equation is set up in a different order. We might have y equals 3 minus 1/2 x. The 3 is away from the x. It has been added. It's a positive 3. That is our starting point, positive 3. So 3 up from the origin is our y-intercept. The x is being multiplied by the negative 2. It's not subtracting 1/2, or sorry, negative 1/2. It's not subtracting 1/2. It's a negative 1/2 multiplying the x. So again, the negative goes with the rise. So from that starting point, we go down 1, and we run 2, giving us our second point. Now, since that is pretty close together, we'll go again. Move down 1, run 2, get another point. And now, of course, we can draw our line through those points. It's not always quite that simple. We can run into equations that look like this. Y plus 3 equals 2/3 x plus 1. All of our equations before were in the form of y equals. This is not. It has y plus 3 equals. Well, we have to solve this just like we would any other equation that we solve for x, but this one has to be solved for y. So we look at what has been done to y. Well, y has had 3 added to it. So to undo that, to take it apart, we subtract the 3. Now remember, when we add or subtract, we must have the same name. So when we do that, we can only do it to pieces on each, we have to do it to both sides, but we can only do it to pieces on each side that have the same name. We are adding or subtracting here 3 ones. We can only subtract that from other ones. So on the right side, we can't subtract it from the 2/3 x. That has the name of x. We have to subtract it from the 1, 1. So on the left side, the 3 is gone. We just have y. On the right side, the 2/3 x is not affected. 1 minus 3 is a negative 2. Now we go to graph it. We start at negative 2. And we have a slope of 2/3. So we rise 2, run 3. And our line goes through those points. We might have 3y equals 6 minus 2x. So again, we don't have y by itself here. What's been done to y here has been multiplied by 3. So to get rid of it, we're going to divide by 3. Now remember, when we multiply or divide, we do not need the same name, which means we can multiply or divide every piece, every digit by the 3. So on the right side over here, each of these, there's 2 digits, the 6 and the negative 2x. Each of them is going to get divided by the 3. So on the left, the 3 divides out, we just have y. On the right, 6 divided by 3 is 2. Negative 2x divided by 3, well, remember we've said that division and fractions are kind of interchangeable. So we're just going to make that into a fraction. Negative 2 divided by 3 is a negative 2/3, and then the x is still on there. So this starts out at a positive 2, and a slope of a negative 2/3, meaning we go down 2 and run 3. to get to that second point. So our line goes through those points. Well, we might have things a little bit more complex than that. We might have we might have 2x minus 4y equals 8. And again, I'm going to step back. Sorry, I'm going to come back to that example. Let's do something a little bit different. One more step I want to go before we get there. Let's do 2y minus 5 equals 3x minus 1. Let's go with that. So here, if we look at what's being done to y has been multiplied by 2, and then the 5 has been subtracted from it. When we go to take that apart, we take off the last piece first. That's the minus 5. So we add 5. Remember, when we add or subtract, we need the same name. We can only do it to one piece on each side. So on the left side, the negative 5 and the positive 5 cancel out. We're left with 2y. On the right side, the 3x is not affected, but negative 1, 1 plus 5 ones is a positive 4 ones, or just a positive 4. Then we need to divide by 2 to get rid of the multiplying by 2. Remember, when we multiply or divide, we can do it to every piece. So the 2 cancels out there, we get y. 3x divided by 2, again, we just turn it into a fraction. 3 over 2 times x. 4 divided by 2 is a positive 2. So we start out at positive 2, right there. 3 over 2x means we go up 3 and run 2. And our line goes through those points. Finally, let's get back to the example I almost did earlier. 2x minus 4y equals 8. If I ask what's been done to y, they say, well, we can't say because there's x over there. We can. The x is just acting as one of the numbers here. We're only focusing on y as the variable. So what has been done here is y has been multiplied by a negative 4, and then 2x has been added to it. So the x just goes with the 2 there as one digit, it's 2x. So to solve this, to take it apart, we subtract the 2x. So that 2x is gone, we just have negative 4y. Now on the right side, however, 8 minus 2x, we can't combine those. This is why we did those rearranging formulas in the last unit. Actually, 2 units ago now. 8 minus 2x is just going to be 8 minus 2x. And then we have to get rid of the negative 4. It's multiplying, so we divide by a negative 4 on both sides. So the negative 4 is gone. We have y equals 8 divided by negative 4 is a negative 2. A positive divided by a negative is a negative. Negative 2x divided by negative 4. Well, a negative divided by a negative is a positive. 2 divided by 4 is going to be 2/4. 2/4 reduces to 1/2. That's a positive 1/2 x. So when we go to graph that, we start as a y-intercept of negative 2. That's our first point. Then we rise 1 and run 2. Since those points are so close together, we'll do that again. Rise 1 and run 2. So there's our line. So there are a lot of application of linear equations. And we might look at, let's say you start 8 blocks from home. And walk away from your home at a rate 2 blocks per minute. Let's graph your distance from home. So if we look at a graph here, we're only going to be using the first quadrant here, which is very typical. I'm going to actually number by twos. 2, 4, 6, 8, 10, 20, 30, and we'll stop there. On bottom, we'll go by 1 minute. 5. So the bottom here is minutes, and this here is blocks from home. So if I'm graphing this situation up here, we start out 8 blocks from home. So when we start, we're at 8 blocks from home. Time equals 0. That's our y-intercept. The y-intercept is a starting point. It occurs where x equals 0. In most cases, the independent variable, which is this horizontal variable, is going to be time. So it's time equals 0, or again, the starting point at the beginning. Now we're moving away at a rate of 2 blocks per minute. So if I go 1 minute, I've gone 2 blocks, that's going to bring me up to 10 blocks from home. If I go 2 minutes, I've gone another 2 blocks, I'm at 12 blocks from home. 3 minutes, I'm at 14 blocks. And I keep going every minute, 2 more blocks from home. And we get that line. That 2 blocks per minute is a rate. We can see that becomes our slope. The slope is equal to the rate of change. And I could keep going with that, or I could use it to write my equation. Y equals, my slope is rate of change, 2 blocks per minute, so that'd be 2x. Plus, I have a positive 8 was my starting point, plus 8. That expression expresses our distance from home. We might have graph the volume of fluid in an IV bag. So I'm going to start off and make my graph down here. Let's be a little bit more precise than that. So let's say we start with 1,600 milliliters in the bag and flow at a rate of 20 milliliters per minute. Now that was a very rapid flow, by the way, but in order to make this example work for us, so I'll put my minutes along bottom here. Okay, so we start at 16 milliliters. That's my y-intercept. It reduces at 20 milliliters per minute. Well, this graph is marked at 100 milliliter marks. So to go down 20 milliliters for 1 minute is difficult to do. But what I can do is this. Since it's 100 millimeter marks, I'll do 100 divided by 20. That would be 5 minutes. It would take 5 minutes to get 100 milliliters. So I'm going to drop 100 milliliters and go over to 5 minutes right here. Drop another 100 milliliters, go over to 10 minutes. Drop another, go 5 more minutes over to 15 minutes. Now another 100, and continuing on. Didn't do a very good job drawing my line through my points, but you get the picture. So the equation here, y equals 1600 is my starting point. Then I was reduced by 20 milliliters every minute. So x is my number of minutes. This equation can be used to predict. If I asked, let's go down further here. I'll go below my graph. How much would be in the bag after 60 minutes? Well, my equation, y equals 1600 minus 20x. 60 minutes, well, minutes is the horizontal axis or the x-axis, so 60 would go in for x. Y equals 1600 minus 200 times, instead of x, I put in 60. Or sorry, 20 times instead of x, I put in 60. So now, it's just order of operations here. Y equals, there's nothing happening to the 1600, but negative 20 times 60 is a negative 1200. And now I can combine 1600 minus 1200 is 400. So after 60 minutes, I would expect there to be 400 milliliters left in that bag. I might ask, how long until the bag hits 1,000 milliliters? So again, we start out with our equation, y equals 1600 minus 20x. But now the 1,000 milliliters here, that is the y variable. The volume in the bag is my dependent, or y variable. So the 1,000 goes in for y. 1,000 equals 1600 minus 20x. And now we have to go ahead and solve for x, just like we would in any other equation. So we're going to subtract the 1600. 1,000 minus 1600 is a negative 600. Equals, here the 1600 is gone, we have a negative 20x. And now we divide to get x by itself. We're going to divide by negative 20. Negative 600 divided by negative 20 is 30. Negative 20 is divided out here, giving us x. X equals 30. That's saying it would take 30 minutes for that bag to be depleted down to 1,000 milliliters of fluid. So I got through the material a little bit faster today than I did last week. Second time through, I always do tend to go a little bit quicker. This is most likely material you guys have all seen before anyway. Coming up, we plan to look at, on Wednesday, we're going to explore that idea of slope a little bit more, different methods of finding slope. We're going to find slope from a graph, slope from 2 points, slope from an equation, which we've already kind of found it from the equation. But we're also going to look at other forms of linear equations. What we looked at mostly today was graphing form, that y equals a slope we use the letter M to abbreviate slope, times x plus a y-intercept. We usually use the variable b as the y-intercept. Now, if you get in statistics, though, you should use the letter A as the slope. B would still be the y-intercept. It's the same concept. And we did actually sort of look at standard form. This is graphing form or y-intercept form. We sort of looked at standard form where we had ax plus by equals c, or sometimes written as ax plus by plus c equals 0. Some people strictly hold the standard form as being held equal to 0. We're going to maybe deal a little bit more with that. In fact, we've got a few minutes today. I might deal with that standard form yet today. And then we're going to look at another form that's a little lesser known called point slope form. In point slope form of the equation, it's y minus, we're going to label it y1, which is a y-coordinate of a point, equals our slope times x minus, we're going to call it x1, which is an x-coordinate of a point. That is a line that has a slope of m and goes to the point x1, y1. We'll look at that a little bit more. Let's explore this standard form a bit. So we had an equation here of, let's just do 2x plus 3y equals 12. This is standard form. Now we could rearrange this. We did it earlier today. We solved it, got in that form of y equals so we could graph it. But there are things that we can look at in this standard form. If we look at this ax plus by equals c, some things we can read directly out of that. One is the y-intercept. The y-intercept is just going to be the value of c divided by the value of b. So up here, c would be 12, b would be 3. 12 divided by 3 is 4. So the y-intercept of that equation is positive 4. A value we have not used is called the x-intercept. X-intercept is the value of c divided by the value of a. So in this equation, c is still 12, a is 2. 12 divided by 2 is 6. So there at x equals 6, that is the x-intercept, or where it crosses the x-axis. We don't typically use that a whole lot, although it is an important concept. It's sometimes referred to as the root of an equation, because it's where the independent value equals 0. When we get into parabolas, the roots are very important for graphing. The last thing we can find from that standard form is the slope. The slope is equal to the opposite of the value of a over b. So up here, a is 2 and b is 3. So the opposite of 2 would be a negative 2 over 3. So negative 2/3 is our slope. So if we go down 2 over 3, your point, we kept going down 2 over 3, we get another point, and notice that's actually our x-intercept. And our graph then would go through those points. We could have actually graphed it with just the x and y-intercept, but I wanted to show you how the slope works in and gives the same line either way. When we get into higher order situations, more complex applications, something called linear programming is very common in statistics and operational research applications. A lot of times we do just use that x-intercept and y-intercept to get a quick graph of the line so that we can then use it in our applications. So anyway, we will come back more to this other stuff on Wednesday. For right now, we've already had on page 205, I think I wrote it down wrong, though it's page 215, 1 through 3, just identifying and reading graphs. And off of what we've done today, page 213 through 217, 1 through 15, the odd, and page 221 through 222, 1 through 15, the odd again. Give you a chance to work on those. And again, if you have not completed Unit 3 test, please make sure you have that done by Wednesday so that we can discuss any questions you might have. We have a couple minutes here. Is there anybody that had anything, was struggling with anything on the Unit 3 test? I know I had a couple of messages. I was in session on Wednesday last week, but nobody came in for questions. So I wanted to make sure everybody got those answered. Does anybody still have any questions they want me to go over?